All right. So good morning, everyone. Today we will be presenting our solution to this year's M3 challenge problem, defeating the digital divide. In terms of our overview, our solution consisted of a variety of methods that address the crux of the problem. We first analyzed cost factors and developed a regression model to predict the cost of internet for consumers in the US and UK over the next 10 years. Next, we developed a simulation that modeled bandwidth usage in order to find the minimum bandwidth needed for different households. And finally, we created a criteria and geometry-based model to optimally place cellular nodes in a region.
So beginning with the first problem, we created a regression model that tied together three crucial elements to determine the cost of internet over the next decade. For our assumptions, we assume that there are no significant policy changes in the aforementioned time span and that the cost per unit of internet is constant, regardless of quantity purchased by the consumer. Additionally, we assume that the US and UK follow similar trends in internet usage, cost, and population density. We also utilize the average growth rates and population density and the cost of living index.
Our regression model utilized three components to accurately determine a cost value. The first factor in our regression model, population density, helps account for the variance in quality and cost of internet. Since internet providers face decreasing marginal costs and economies of scale, we expect areas with higher population densities to have cheaper costs compared to less dense regions. Next, we included cost of living as a metric to consider the variations in pricing across a region. Simply put, expensive areas such as New York City have higher prices for all services such as internet plans. Our model accounts for these variances as well as expected changes over the next few years, covering all financials for the problem. The final factor, average download speed, helps determine the quality of internet infrastructure for each state. Areas with faster download speeds and well-established internet grids operate more efficiently with less costs. Combining these components leaves us with the framework for our solution to the first problem.
We also understood that in order to determine the cost of internet over the next decade, our regression factors had to adjust accordingly. Starting with the change in the cost index, we factored in the rate of inflation by using online data to predict an average inflation rate for the next decade. We also expected the average download speed to increase over the next decade because of technological innovations and Moore's law. To adjust for this, we created two exponential regression models based on the provided download speed trends for both countries to predict the values over the next 10 years. All of these factors were used in the final random forest regression model.
To model the internet cost over time, we trained a random forest regression model, a machine learning algorithm on a dataset of 48 mainland states with their population densities, cost of living values, average download speeds, and internet costs. The random forest works by creating a set of decision trees, each of which creates a series of logical splits that maximize information gain in order to predict the cost. The outputs of the individual trees are averaged for the final ensemble prediction. By following the splits created during training, the model is able to produce a regression output for new data points. Our random forest model consists of 20 decision trees, each limited to a maximum depth of 5 nodes to improve generalization to unseen data. Ultimately, this model is able to predict the cost per megabits per second given a region's population density, cost of living, and average download speed. By using the initial conditions for the US and the UK and applying the model with the appropriate changes and factors over time, we found that the cost of internet per megabits per second will decrease by 13.16% and 17.92% for the two countries over the next decade. This result is consistent with our expectation that improvements in infrastructure and technology will decrease cost. Our model also gives a lower estimate for internet cost in the UK, which is consistent with the correlation between higher population density and lower cost.
All right, so let's move on to question 2, bit by bit. In this problem, we were tasked with finding the bandwidth required to meet the demands of 3 different scenario households, 90% and 99% of the time. To do this, we ran a simulation of internet usage over a week for all 3 households. To successfully model this problem, we made several key assumptions. Our first assumption is that all days of the week are the same. For example, we don't count weekends differently than normal weekdays, which allows us to apply the same simulation process for each day and hour in a uniform manner. We also ignore any special circumstances like holidays that can greatly change internet usage patterns. Our second assumption is that people are awake 16 hours a day. This results in simulating 112 hours for each week and allows us to determine the probability that each task is performed at a specific hour. And our third and final assumption is that users don't multitask. This simplifies the simulation as it avoids dealing with assigning multiple tasks to any one user.
So our model consisted of a simulation run in Python, which would simulate the 112 waking hours in a week. For each hour, every single member of the household would be assigned a task. The hourly household bandwidth usage is calculated as a sum of the bandwidth used for all the tasks performed during that hour. At the end of the 112 simulated hours, we recorded the maximum of the hourly household bandwidth usage as the required bandwidth to meet the demand for that week. Repeating the simulation along with finding the 90th and 99th percentile in the distribution of data allows us to uncover the bandwidth required to satisfy demand 90% and 99% of the time. And on the slides, we can see the three scenarios that were given for the problem. So to determine tasks for a given hour, for each person, we came up with a table of their internet tasks and how many hours a week they spent on the task using the data provided. We then divided each task by the 112 waking hours to determine the probability that the user would be performing that task at any given time. Each hour, a random task is picked using the previously calculated probabilities. For that hour's bandwidth usage, each task was assigned either a fixed bandwidth value or a range of values or a random value within the range is selected from the data provided in the data sheets. So for example, the 2 to 11-year-old spends about 25 hours in school, which translates to a 22.3% chance that the child is in school utilizing video conferencing at any given time during the week. This is then translated into a random amount of data usage between 2 and 5 megabits per second for that hour.
Here we show a part of a simulation of bandwidth use for a 2 to 11-year-old over a week. In particular, this could have been used for scenario 1. In the first hour, the child uses video conferencing for school, which takes 3.5 megabits per second. In hour 2, the child doesn't use the internet, which takes 0 megabits per second. In hour 3, the child watches traditional television, which takes 6.5 megabits per second. And in hour 4, the child doesn't use internet, and again, there's 0 megabits per second internet demand. We then fast forward to the end of the simulation, where at hour 110, the child has school again and uses 4 megabits per second. Note that this is different from the demand in hour 1, as data usage can vary even when doing the same task. This type of simulation was repeated for 1,000 trials, giving us 1,000 values for the max megabits per second required in a week. The 90th and 99th percentiles represent the bandwidth required for 90 and 99% of the simulated household's demand.
So for each scenario, the distribution of the 1,000 data points were plotted on a histogram, and vertical lines were inserted to show the 90th and 99th percentile. We found that 14.5 megabits per second was the bandwidth necessary to support 90% of internet demands, and 15.5 megabits per second was the bandwidth necessary to support 99% of the internet demands in scenario 1. For scenario 2, it was 20.8 and 21.8 megabits per second. For scenario 3, it was 20.6 and 21.9 megabits per second. The FCC's broadband guide for moderate internet usage in households of 2 to 3 people recommends internet service between 12 and 25 megabits per second, which is fully supported by the results from our model.
For question 3, we needed to optimally place 4G and 5G towers in the given regions. Our first assumption was that the price of 5G internet plans are constant across different regions. Due to the high barriers of entry in the realm, prices tend to remain constant around the $89 mark. This was the cost we used in our models. Our next assumption is that population densities are constant throughout an entire subregion for a given subregion. This is because the data provided did not include deviations in population density across the region. Our third and final assumption is that walls and other natural barriers will not hinder 5G speeds inside their effective range. This is because it's nearly impossible to accommodate for the different materials and the effects that they will have on the signal.
Moving forward, the differences between 4G and 5G internet were crucial in defining our approach. 4G towers have longer signal ranges, slower speeds, and are less expensive compared to 5G towers. These contrasts led to slight variances between determining the placement of 4G and 5G nodes. For 4G internet, we used a center of mass model to determine the geometric center for each region. For 5G internet, we added on a selection-based model to first locate suitable areas for the more costly technology and then proceeded with the same center of mass model. We will now explain each of the models in further detail.
So on this screen, we've largely outlined the steps needed to take in order to find the center of mass for a given region. As seen in the top right corner, in order to find the actual XY coordinates of the center of mass, we first need to calculate the moments of the regions about the X and Y axis, which are represented by mx and my respectively. In the bottom left, we have the following defined double integral expressions for mx and my. Though the actual regions are not defined by any specific function, we can get a rather accurate approximation using Riemann sums, which is done by plugging in all of the centers of the squares contained in the region, as shown in the bottom right corner. Moreover, since we assume population density is constant, we can actually set it equal to 1 for convenience of calculations, as it will be canceled out when we divide mx or my by m to get the coordinates of the centers of mass. In particular, this means that the mass of a region will be equal to the area. And this is very convenient as the area of each region is directly given in the data sheets. Now, let's move on to an actual sample tiling. We will be finding the center of mass for subregion 2 of region C. So we first need to approximate the psi length of the tiling, and this can most accurately be done with subregion 3. Suppose we let delta x be the psi length of the unit tiling square. Then the approximate psi lengths for subregion 3 are 2.5 delta x and 8 delta x. Multiplying them gives the area of the rectangle, which is given from the data to be 0.1 square miles. And this gives delta x to be approximately 0.071 miles. Now that we've gathered all of our data, it just remains to plug our numbers in. All the points that were put in set P are marked accordingly on the graph to the left, and plugging these points into the summation expressions for mx and my give 1 over 289 delta x and 1 over 267 delta x respectively. After that, we can just plug in delta x to get the xy coordinates of the center of mass, which come out roughly to be 0.225 and 0.169 miles respectively.
Unlike the well-established 4G internet infrastructure, the newer 5G network brings forth more logistical barriers and costs, leading us to create a selection-based model that pinpoints the most optimal regions for 5G. This model takes in 2 factors to determine whether a region is befitting for 5G internet. Because of the high initial investment of owning a 5G device and affording a continual plan, the first factor relates to household income. There's no point in building a 5G network if there aren't enough consumers intending on using it. Thus, we turn to consumer wealth by deriving a formula using data on the average percent of income consumers allocate towards their internet plans, in addition to the average cost of a 5G plan. Setting up and solving this equation yielded that the minimum average household income for a region to be suitable for 5G internet should be roughly $104,000 US. Population density is a second component in our selection-based model. Since the 5G towers have significantly shorter ranges, it is crucial to optimize the amount of consumers in a given area. We use the average population density for an urban cluster as a benchmark in our model, which comes out to be at least 777 people per square mile. Now, let's put this model to the test by looking at the sample regions in the M3 dataset. As shown on the table, only the C subregions have a high enough population density and average household income to be eligible for 5G internet. Taking subregion C6, for example, we would locate the 5G nodes by applying the same center of mass approach as previously described. In our initial report, we described this process taking place over the entire subregion, but after some thought, we realized it would be more beneficial to break up the subregion into smaller areas to adjust for the smaller ranges of 5G towers. To recap, the 5G selection-based model allows us to locate the region suitable for 5G based on wealth and population density. Once a fitting region is identified, we then proceed with our center of mass approach to find the exact locations for the nodes. This model ensures that we optimize the type and usage of internet across a country or continent.
Thank you to all the icon creators, sponsors, and judges for this opportunity. And with that, we want to open the floor to any questions.
Before we have any questions, I think we want to say thank you. Very nice job. Excellent.
That was very nice. Thank you. I got a couple questions about your simulation for the second question. The first is when you divide up a day in terms of different segments, do you make up in terms of the program, do you make up a plan for what the person's going to do for the whole day, or do you treat each segment as if it's independent? And the second part is you assume that um, um, they're only doing one thing at a time. They're not multitasking. How would you adapt things if you did allow for multitasking?
So yeah, for your first question, we treated each block independently, and we do recognize this as one limitation of our simulation. But it would have been like a lot more difficult in order to like block out certain times, because obviously if you're taking school, for example, it wouldn't like occur during 1 hour block, and there would be like, I don't know, they'd watch TV and then another hour block. So obviously, in order to like actually make it make sense, it's a lot more difficult. So we took this approach where each block was independent from each other. Could you repeat the second question again?
It's about multitasking. How would you adapt things if you allowed for multitasking?
I think for multitasking, of course, it would also be a bit harder because obviously each person could do multiple tasks. Sometimes they do one task, sometimes two tasks. But I feel like in order to account for that, we could have added maybe like a factor that added some randomness to the data usage. So for example, if you're using school, we gave out a few numbers. I think it's like 0.5 to like 5.5 megabits per second, but then we could also add like perhaps like a random amount of megabits per second from maybe like 0 to 2 to account for like other tasks, like maybe they're using internet browsing for their school things, and that would allow us to perhaps adjust the data usage for that hour for multitasking.
Okay, thank you.
I'm wondering if you can take your presentation back to the sort of your solution to question one that has the prediction out 10 years. That's it. Excellent. So I'm seeing an awful lot of fluctuation, especially early on in like, if we had asked for you to predict not instead of 10 years out, or 5 or 10 years out, if we had asked you to predict like 2 or 3 years out, I feel like your models were going to produce us something totally crazy. And I guess my question is, do you have can you speculate any reason why these have so much fluctuation? And is this sort of, is this a result of the machine learning? And is there a particular reason why you use this like deep learning model instead of just doing sort of standard regression sorts of fits?
Yeah, so for the first part, the variance can be improved by simply using more data. Like in the time limit of the competition, we were able to collect the data for 48 US states, but of course 48 data points. If we had more data, then the model would be able to improve its accuracy in the short term and in the long term. So we recognize that as a limitation of our approach that we took during the competition. And we also felt that we used the machine learning model because we felt it was more efficient in terms of our time to have the model be able to recognize the solution, especially since we're using factors like population density, which are very skewed and nonlinear, and it'll be very difficult and time consuming to sort of like apply transformations to this data and then use more traditional models for that.
I have a follow-up question to that. So in some sense, like there are just the 48 or 50 states that you have data for. So even given more time, we're not necessarily going to be able to get more data points if you have one data point per state per year. So with that in mind, what could you do to help with this fact that you might not have data available and you might never have that data available?
So we were thinking that we could also expand this to not just include the US states. It could potentially include other countries, or it could even include smaller representative samples of states. For example, we were thinking of maybe even doing the county level, since of course a county could represent a larger area, given that a county has both rural and urban areas. And so I think we can get more data just by decreasing sort of the size of the region while keeping it as representative, and also being able to acquire more data from other places.
Yeah, that makes sense to me.
I'm gonna jump in and ask a question about your solution to the third question. In particular, when it came to determining the 5G towers, you had that really tied to household income. And I'm just wondering, now that you've had some time to think about it, and make believe you had access to any information that you wanted and any data you wanted, are there other things that you would consider or you would take into account when you're determining whether a region needs a 5G tower?
Yeah, so I think a lot of it comes down to like specifics for a certain area. Like one of the things with 5G we mentioned as a limitation or a model was like the walls and barriers and stuff. And there's like a reason why like cities like New York City don't have 5G to the extent that like Philadelphia does. A lot of it kind of comes down to like a city's specific like establishment with like how open it is and where like nodes are accessible. Because unlike 4G towers, 5G nodes are placed on things like traffic lights or anywhere like those sort of locations aren't really built in. So I think that like a lot of that sort of comes down to like looking at a city individually and determining like a one-on-one basis if it's suitable for 5G, using a lot of the things that were kind of limitations in our model.
Thanks.
Let me follow up about that, because I was worried about the placement of these towers also. In part 2, you figured out how much bandwidth people need. But in here, you place the towers on the basis of who could afford them, not what they needed, if I understand you right. The basis for placing the towers is based on the income, not the needs. Is that right?
Not exactly. I think what you're kind of alluding to is like the income determines whether, like, let's say we're looking at a subregion, right? We want to say, is it worth putting 5G internet in that subregion? So that's where we take a look at the income. The actual like placement of the 5G nodes and 4G nodes is a center of mass, which basically says that in a given area, like how can we maximize the radius for the tower? Because each tower has like a certain radius. And if you place it in the center of mass for that region, you're maximizing the distance, right? Because if you put it on the edge of a subregion, like half of it goes to like water or somewhere else, or if there's overlap, there's no point in doing that because you're not maximizing the efficiency. So that's where that was like our approach with that. And I think the income part ties in just with like determining whether a subregion is eligible for 5G.
Did you use the models you developed in part 2 for part 3?
No, I think a lot of that kind of goes to like, if let's say there's one household that has like 5 kids and they have a high internet demand, and there's another house that's like 2 elderly people who don't really use the internet, but they're still in the same area and they can definitely be in the same area. It's pretty difficult to kind of predict that, especially for a certain subregion because of the variances in different households. So unless like we could generalize and say that, okay, this town is known for having people, like teenagers who use a lot of internet, then we could adjust that. But based on just the general like factors we looked at, it was really hard because it was just an individual sort of thing for each household.
Okay.
I think we have time for one more question.
Well, I could ask a technical question about part 2, which was you ran a Monte Carlo simulation, and then you had some nice plots where you showed how you looked at the 90th and 99th percentile. Yeah, you can go back to that, I guess. So when you ran the simulation, how many times did you run it? How many iterations did you run it for? And how did you choose that number? And how did you know that was an okay choice?
Well, as we stated previously, the simulation, it was run for 1,000 trials, and we just thought that it was like a pretty large number of times to run the simulation. And obviously it gives like really nice numbers for the 90th and 99th percentile. Like once you sort all the data, you can just look at the 990th data point and the 900th data point in order to get, you know, your percentiles. So, and obviously like 1,000 times like a lot. So we decided that that would be suitable for our purposes.
If you weren't sure, what could you do to maybe check to see if that was the right number?
I feel like we definitely could have tested like a lot of different numbers and seen like how the results may have changed. Like if our model would be like robust enough to like account for these different number of trials, and also just running like maybe 1,000 so 1,000 trials in simulation, but doing it several times and also comparing the results there to see if it was suitable.
Okay, great.
I think that might be all that we have time for. I just want to remind you that among the hundreds of submissions that we got for this year's challenge, yours was among the top 6. And so all of the judges that are on this call today and all of the judges that couldn't be with us today are incredibly proud of your work and so grateful that you're here with us today. And so with that, I think I'll close things out and I look forward to seeing you later this afternoon at our awards ceremony. Thank you.
Great job.
Thanks so much. Great
Thanks,
job.
guys.